Here are some problems involving four of the colligative properties. So first let's look over the problem involving vapor pressure lowering. So in this particular case, the solvent alone will have a vapor pressure. That's usually temperature dependent. And the minute we add a solute, the vapor pressure is going to get lowered. Again, when you have a solute and a solvent, you have to break up those interactions as well as solute-solute and solvent-solvent interactions, henceforth more interactions to break free a lower vapor pressure. So a typical problem that involves colligative properties, the one that is implicated in vapor pressure lowering, is something like this. So you're asked to calculate the vapor pressure of a solution, okay, solute plus solvent, when 25 grams of urea. So here's the structure of urea. From here, you should be able to get the molecular weight of urea. So 1 mole of urea actually has about 60 grams of urea, getting that from the periodic table. So you take 25 grams of urea and add it to 525 mils of water. The temperature is 25 degrees C. First thing you want to do is identify the solute and the solvent. So very easily, the urea is the solute, and water, 99% of the time, water is going to be the solvent. So here's the equation that is utilized to solve this. So we have the vapor pressure of the new solution upon addition of the solute, and that is going to equal to the mole fraction of the solvent. So the mole fraction is a fraction of the mole of the solvent divided by the total moles, so it's a fraction, part over whole. That times the vapor pressure of the solvent by itself, that is P naught solvent. So what is the vapor pressure of pure water by itself without any addition of anything? You can look at a table. So this table will be given to you on any type of examination. So since we're at 25 degrees, the vapor pressure of water at 25 degrees is 23.76. So we can plug in these values here. The new vapor pressure of the solution is going to be the mole fraction, mole of the solvent divided by the total number of moles times the vapor pressure of solvent water by itself. So I went ahead and calculated the number of moles of my solvent water. So in this particular case, you have to recognize you're given 525 mils of water. The density of water is actually 1 gram per mil. That's pretty much a safe estimate, so you can get away with saying that. And the mils cancel. 1 mole of water is 18 grams, and the grams cancel. So I'm getting 29.15 moles of water, which is the moles of solvent. Likewise, let's calculate the moles of the solute urea. 25 grams, so 25 grams of urea. 1 mole of urea actually has 60 grams, getting it from the periodic table for each element, and that's 0.4163 moles of urea, NH2CONH2. So I just plug those values in. Plugging those values in, the mole of the solvent is 29.15. The mole of both solute and solvent is going to be the sum, which is 29.57. That multiplied by 23.76. We got that number from over here, the vapor pressure of water by itself. And we get a value of 23.42 millimeters of mercury. So 23.42 millimeters of mercury upon addition of 25 grams of urea. Upon water by itself, the vapor pressure is 23.76. So yeah, vapor pressure is going to lower. In this case, it lowers from 23.76 millimeters of mercury to 23.42 millimeters of mercury. This equation will be given on the exam, so it's worth practicing these types of problems. Mole fraction times the vapor pressure of the solvent by itself, standalone. We can also solve this problem in a totally different way. We can solve, instead of the mole fraction of the solvent, we can do the mole fraction of the solute and multiply it by the same value, the vapor pressure of the solvent by itself. So doing that particular case, we get the change in the vapor pressure, and the change in the vapor pressure is going to be 0.335 millimeters of mercury. So we know that vapor pressure lowers when we add a solute to a solvent, and so the vapor pressure is going to lower by 0.335, so 23.76, the original vapor pressure of water by itself, minus the change, 0.335 millimeters of mercury, and that will give you 23.42 millimeters of mercury, and that is the same. So you can calculate the change by how much the vapor pressure is going to get lowered, subtracted from the standalone value. That's one method. In this case, you're solving for the mole of the solute. Or you can do it this way, get the mole fraction of the solvent and multiply it by the standalone value. So both methods give you the same answer. Here again, it's the mole fraction of the solvent times the standalone. Here it's the mole fraction of the solute times the standalone. And when you solve that, you have to take the difference because the vapor pressure is lowered. Here's a problem that involves freezing point depression and boiling point elevation. So the problem asks to 6 grams of cyclohexane solvent. So we know that cyclohexane is our solvent because the problem tells us it's the solvent. And we add 0.060 grams of this substance, C6H4Cl2, and it tells us that this is the solute. So we can automatically plug it into our values of our boiling point elevation, which is Kb, the molal boiling point constant times the molality, and our freezing point depression. So these values are the change in, which is the freezing point depression constant times the molality. Remember, lowercase m is molality, moles of solute per kilogram of solvent. So going ahead and calculating the change of in the boiling point, the new boiling point temperature, we'll calculate the moles of our solute, we'll calculate our kilograms of our solvent, multiply that by Kb, the molal boiling point elevation constant, and we get a value of 0.1936. That's our change in the boiling point. The boiling point elevates when you add a solute to a solvent. So the new boiling point is going to be the original boiling point of 80.7 plus our change. So 80.7 plus our change, 0.193, gives us a new boiling point of 80.9 degrees. So the boiling point increases by about 0.2 or so degrees. We can calculate the freezing point depression, which is the freezing point molal constant times the molality. So we do the exact same thing. This time, we multiply the molality by the freezing point depression constant, which is 20 degrees C divided by molal. So solving for that, we get a value of 1.383 or so degrees C. So the freezing point gets depressed. It lowers. So our new freezing point is going to be the original freezing point, and because it's freezing point depression, 6.6 degrees minus our delta T, our change in freezing point, which is 1.383 or so degrees. So 6.60 degrees standalone value for the freezing point minus the change. Because it's freezing point depression, it is going to be lowered by minus 1.38 degrees, and our new freezing point of cyclohexane, when we add this solute, is going to be 5.22 degrees C. So both these equations will be given on the exam, and the freezing point and boiling point constants will also be given on the exams. So this is basically a plug it in and get the answer out type of problem. Make sure you calculate the new boiling point by adding it to the original boiling point. Make sure you calculate the new freezing point by lowering the value according to what you calculate for delta TF. Here's our final practice problem that involves osmotic pressure. So here we have a 202 ml benzene solution containing 2.57 grams of an organic compound. It's unknown, and it has an osmotic pressure of 8.23 millimeters of mercury at this temperature. So calculate the molar mass of the solution. First thing to solve this problem is three things. One, you need the equation, so that will be given on the exam. Second thing that you will need is the gas constant, R, that will be given on the exam. So the osmotic pressure is just the product of the molarity in moles per liter times this gas constant, R, times the temperature in Kelvin. So to solve this problem, we're being asked to get the molar mass. So the molar mass has units of grams per mole. So what I've done is basically solve for molarity M. Given our osmotic pressure of 8.33 millimeters of mercury, I went ahead and converted that to atmospheres. So that's the conversion factor. 1 atmosphere is equal to 760 millimeters of mercury. So that conversion factor will be given on the exam. Dividing this by RT, the gas constant times temperature. Make sure you convert your temperature to Kelvin. And solving for all of this, my units are in moles per liter. So this is my concentration of the benzene solution, moles of solute per liter of solution. Well, how much volume do I have? I have 202 milliliters of this solution. So I'll go ahead and calculate the number of moles. So 202 milliliters converted to liters. And I got my concentration from my osmotic pressure equation. So this is the number of moles that are in 202 milliliters. And I have 2.47 grams of my unknown. Units are grams per mole for molar mass. So I'll take the 2.47 grams divided by the number of moles I got in 202 mils. And I get grams per mole. Doing that computation, I get 27,172 grams per mole. That is the molecular weight of my unknown substance that I put in to my benzene. So in essence, the osmotic pressure here, it's with benzene. Other examples, it's usually with water, but it doesn't have to be with water. Benzene can also undergo a movement or shift in the presence of a permeable membrane and neutralize and solubilize the organic substance. So osmotic pressure, pi, is basically the pressure that's required to stop osmosis. So if you want to stop benzene from permeating the semi-permeable membrane, you're going to need to add 8.23, excuse me, you're going to need to add 8.23 millimeters of mercury at that particular temperature. But here, the utility of this problem is that we can actually get a concentration of a solution and get the molar mass in grams per mole. So you have to remember the definition of molar mass unit-wise is grams per mole, and with that, we were able to utilize this equation to get our answer in grams per mole and get the molecular weight.